So, it is the 9th of March, and we are going to go over the Reaction Type and Activity Series FIP quiz. Okay, so what you needed to do was name the type of reaction, predict the product, balance the equation. And the very first one that we started off with, you were told that lithium nitrate and potassium Whoa!
That's kind of scary.
Okay, so we're told that lithium nitrate and potassium bromide react. What are the possible equation types that this could be? It's double replacement. You have two ionic compounds. Anytime you're looking at two ionic compounds put together and a reaction occurring, you've got double replacement. So the next step then, so we've identified that this is, let me use a color that's visible, double replacement or double displacement, whichever you care to call it. We've identified the type of reaction this is. So now what we want to know is what our products could be. And because these are ionic compounds, we can break them down and look at, oh hey, there's the positive ion in each pair. Oh hey, there's the negative ion in each pair. And so when we end up, we're going to have a positive and a negative ion. So we get out of this potassium nitrate and lithium bromide. This one's really easy because everything here has a +1 or a -1 charge. So they're all balanced. So you can say, hey, there's the equation, there are the products, it's already balanced. Okay, so that one was fairly easy. Already balanced. Predicting the product, it's just straight up ionic compounds. Questions on this one? Yeah? 9? Okay. So here, we're given a single compound, Fe2O3. And, nope, there. We're told that it reacts. There's only one option for reaction type. What would that be? Decomposition. It's breaking apart. You've got a compound and it's going to break apart. Now here's the thing, and this was one where a lot of people made a mistake. So I want to stress this. When this decomposes, it has to decompose into those elements in the form in which they exist in nature. So, in what form does iron exist when it's iron all by itself? Just Fe. Scary metal man walks alone. So this is, and we'll write down here, this is a decomposition reaction. In what form does oxygen exist on its own? It's a gas, but it's also a diatomic molecule. So that's O2. Okay. So what some people wanted to do was write, oh, this breaks up into Fe2 plus O3. No. It's not going to decompose into some sort of weird hybrid diatomic iron and an ozone molecule. It's not going to do that. So you cannot do that. What that means, of course, is that you then have to balance the equation. And I always, for some reason, I love the decomposition of iron 3. This is iron 3 because it looks like this. 2 Fe2O3 yields 4 Fe plus 3 O2. And because it's got the 2, 3, 4, not in that order, but I don't know why, but I always like that one. It's a common when we balance it again and again. Okay, questions on that? Most common mistake people made here was trying to break that into Fe2 and O3, and that's not what happens. You have to always look at either the compounds that these things would make on their own, you're back to compound formula writing, or in what state they exist on their own out in the wild. Okay? Yeah, and the keys here are the fact that metals are always by themselves, and the heavenly 7, oxygen, hydrogen, nitrogen, chlorine, fluorine, all those, are always diatomic. So that's what you got to look at. Okay, so we have ammonium fluoride plus chlorine gas. What kind of reaction could we possibly have here? It's got to be single replacement, because here you have a compound that's an ionic polyatomic ion plus a halogen, and here you have a halogen. So what's going to replace what? The halogen will replace the other halogen. Okay, so we know that this is single displacement or single replacement. And now we just have to predict products. So we said the halogen will replace the other halogen, so we're going to end up with a compound of ammonia, the ammonium ion, NH4, partnered with chlorine. But here's where people made their big mistake. If we have an NH4, 1 plus ion, and a Cl, 1 minus ion, what compound do they form? NH4Cl. So you can't take this subscript from the diatomic chlorine and carry it along, because that's not the compound that they would form. And you have to look at each one as a new compound that's forming. So then what form does the fluorine take? F2. It's a halogen, it's diatomic, so the fluorine, and I mean it's going to be gaseous, yeah, that's fine, but the big thing is knowing that when they form new compounds, they do so according to all the rules that you've already learned and practiced about how substances form compounds, based on what kind of ions they'll form, or how they exist on their own. So now you have to balance this thing, and this is pretty easy. 2 ammonium fluoride plus 1 chlorine molecule gives us 2 ammonium chloride plus a fluorine molecule, and those would both be gaseous. That's it. Not too bad. Single displacement. Okay, questions on that one? Okay, so here we have magnesium and oxygen gas. What's the only, well, what kind of reaction could we run here? Okay, this is one where it's 2 different kinds of reaction, because it's synthesis. We have 2 individual elements coming together to form a compound, but it's also a combustion reaction. We can actually run this reaction, if I could ever find our magnesium ribbon again. We used to run this. If you burn magnesium, this is the reaction you're running. Magnesium metal is fusing with oxygen gas and forming what compound? Magnesium oxide. So again, when we write the compound, we have to think about the fact that magnesium is a 2 plus, oxygen's a 2 minus. What's our compound? Just MgO. Okay. Now, of course, that means we have to balance. Oh, and this is combustion and synthesis. So this is MgO. We get 2 Mg plus an O2 yields 2 magnesium oxides. So 2 moles of magnesium, 1 mole of oxygen gas, and this would be a gas, of course, yields 2 moles of magnesium oxide. Okay, questions on that one? Okay, this is C3H8, propane and propane accessories. Combining with oxygen. What kind of reaction is this? Combustion. And some of you even said it's a combustion of a hydrocarbon. Yeah, we can combust a lot of things, but we run these combustion of hydrocarbon reactions fairly frequently. And this is just combustion of a hydrocarbon. You have a hydrocarbon and you have oxygen. They're the only 2 things. And there's no way to do this other than to memorize the fact that every time you combust a hydrocarbon, you get 2 products. Name them. CO2, H2O. Whoops. CO2 and H2O. And if you, has anybody ever told you that if you drive your car like a half a mile a day, every day, and that's all that you drive it, that's actually hard on your exhaust? Why is that? What are you doing inside your engine? Combusting a hydrocarbon. You're burning a hydrocarbon. That hydrocarbon is gasoline. What are the products of hydrocarbon combustion? CO2 and water. When an engine is cold, that water condenses inside the exhaust, and you have sitting water in there. So if you only drive the car like a quarter mile or a half mile a day, you'll end up with water laying in your exhaust. Of course, then that water provides an environment where the metal can oxidize or rust, and you get a rusty exhaust. If you drive the car a little bit further every day, the exhaust has a chance to do what? What happens? Anybody ever touch a hot exhaust? This is really common if you've ever ridden mopeds or motorcycles. The leg burn from the hot exhaust. Yeah. The exhaust tends to heat up because the gases coming out of the engine are hot. And so once the exhaust heats up, it's not a problem because that water vapor passes out of the exhaust system and it's not condensing on a cold metal. So that's why, if you only drive your car like a quarter mile a day, you need to warm it up until the exhaust is warm enough that you don't have water sitting in your tailpipe. Just a little bit of a connection there. Okay, so it's a hydrocarbon combustion. The only products are CO2 and H2O. Now we got to balance. Okay, so we've got our balancing here. Easiest, what are we going to balance last? Always think about that. Oxygen. Because you've got that O2, it's easy to fix your oxygen at the end. Hydrogen seems like the obvious thing to balance first. For some reason, if we put 4 in front of the water, we get 8 hydrogen. 4 plus 2 is 6 oxygen, because we have 4 oxygen here, 2 oxygen there. So now everything's balanced, but, we need to balance our carbon. If we put a 3 there, now that's balanced. We now have 6 oxygen and 4 oxygen, that's 10 oxygen. Stick a 5 out there and we're good. A few tricks for balancing hydrocarbon combustion reactions. The coefficient in front of the CO2 in the product will always be either the same as the subscript or 2 times the subscript. The coefficient in front of the water will always be either half of the subscript or the subscript itself. So those are the 2 things to look for, and you can basically run those 2. At some point I'll have you balance all the combustion reactions for hydrocarbons from methane, which is a 1 carbon, up through decane, which is a 10 carbon hydrocarbon. And it's, this is for the straight chain hydrocarbons. It's different when we get into other stuff. Okay, questions on this? All right. Okay, hydrogen gas plus oxygen gas, we put them together, and what do you get? Bibbidi-bobbidi, water. Okay, it's funny in my head. So, what kind of reaction is this? You got 2 single elements coming together. They're going to form a compound, obviously. There's nothing else they can do. Synthesis, but it's also combustion. So this is a synthesis or composition. It's also a combustion reaction. This is the combustion of hydrogen gas. Are you familiar with the Hindenburg? Yes, hydrogen is lighter than air, but holy moly, is it flammable. The Hindenburg was a giant combustion of hydrogen reaction. And it turns out there was a spark from the ground. Vehicles that travel through the air that have metal frames, such as airplanes, there's very often an electrical potential difference. There are more electrons on either the ground or the clouds than on the other. The charges are not balanced. And so you get sparks of static electricity leaping from clouds to ground, do you know what those are called? Lightning. That's lightning. Lightning is giant sparks of static. If you've gotten shocked on a doorknob, that is micro lightning. So you can walk up to your siblings now and go, micro lightning, or something similarly stupid and geeky if you're into that sort of thing. When you have metallic vessels traveling through air, they are prone to building charge. If you get into physics, there's a whole reason for that. But anyway, so vehicles have to ground. They have to discharge extra electrons. And there was something with, I forget exactly what the explanation was. There was something with like the grounding system on the Hindenburg. It didn't. And basically a spark leapt from ground to the vessel. And a spark is really all it takes to get that. So ground straps. This is why they matter. Okay, so this is a synthesis reaction. It is also a combustion reaction. What is the product of the combustion of hydrogen? There's only one. Water. H2O. So we balance that. We take 1 mole of hydrogen gas, 2 moles of hydrogen gas, 1 mole of oxygen gas. We get 2 moles of water out of that. I do, in watching the footage of the Hindenburg now, I wonder if there was well, no, it would have been vapor. I'm going to say, no, there wouldn't have been a puddle under it. This comes off, I mean, you look at the kind of temperatures at which that is combusting, this water is going to be gaseous. So you're going to have water vapor. Okay, questions, comments, concerns on the quiz. If you made mistakes, do you see why you made them? Okay. Most of the mistakes I saw were, the category I'll call dumb mistakes, which is great because they're the easy ones to fix, and now you've got them out of your system.